So, welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, let me briefly recap the previous lecture. So, in the previous lecture we talked about frequency dependence, in real dielectrics, and there we said that you have we defined dielectric properties in terms of complex behavior. So, we defined this kappa as kappa prime minus kappa double prime. So, this is the real part and this is the imaginary part. So, basically this real part represents the charging current and this imaginary part represents the loss current. So, basically these are frequency dependent components. In addition, you will have frequency independent components which is separate, and the ratio of these tan delta is kappa double prime minus kappa prime. You can also write this as epsilon r double prime divided by epsilon r prime. So, the ratio of these two is tan delta. So, for a lossy system we will have high tan delta for a lossy system. Basically what it means is that if your system has high epsilon r double prime, which means it has high frequency dependent loss current. So, high epsilon r double prime will mean high frequency dependent loss current, and what this would also mean is that your power loss will also increase. So, for dielectric materials you have epsilon r double prime which represents the actual dielectric behavior, whereas epsilon r double prime represents the loss behavior of a dielectric. So, these are taking the frequency dependent parts into consideration. On top you might also have ohmic losses. So, the total losses have to be calculated by combining ohmic losses plus the non-ohmic frequency dependent losses. So, this is what we have done in the last class, and we determined a framework to do that. Now, what we will look at is the frequency dependence at the microscopic scale. Frequency dependence okay. So, we saw that earlier your dielectric constant varies like this. So, you have frequency, you can write f omega or f, then we have epsilon r. We will plot it as, now that we know it is a real and imaginary part, we will plot the real part. This is what we plot here as. So, initially we just plot the scalar part, but here we know that it is a real part. So, this varies in this fashion. Like this. Okay. So, at high frequencies your dielectric constant is 1, at little bit lower frequencies your dielectric constant is epsilon r prime electronic. Here it is epsilon r prime ionic, this much, and here it is anything on top of 1 is this, and this becomes epsilon r prime dipolar, and then we have interfacial, right. That is what we said earlier. Now, we see some interesting features here. The interesting features are that at high frequencies, when you transition from 1 to epsilon r electronic, there is a resonance kind of peak. What is the reason of this resonance? Similarly, as you transition from electronic to ionic, you see again a similar resonance kind of peak. These are the peaks also encountered in mechanical oscillators. When you have a resonance, you have these kind of resonance peaks. So, we will model this ionic and electronic polarization on the basis of basically harmonic oscillators. Okay. So, these are two, we will call them at resonance peaks, and we will see how they come about. And then when you go to lower frequencies, you do not see resonance peaks as well, but what you see is a slow decay of the electric constant. This is called as a relaxation, because here at the molecular level there are statistical events in response to time, and basically when you have electric field applied and when you have a certain frequency of it, the dipoles, as you go from lower to higher frequency or higher to lower frequencies, they take time to align themselves in the direction of applied field, and they are, because this is because the dipoles are heavier, they have certain, you can say, if you like, you can call it friction in the lattice, and they have to go from one stable state to another stable state. So as a result, there is an energy barrier to be crossed. So as a result, they slowly relax from one position to another position, and that is why it is a time taking process, and this process is called as a relaxation. So we will look at these three phenomena. We will not go into details of interfacial. We will look at mainly dipolar relaxation and resonances related to harmonic resonances related to ionic and electronic polarization, considering simple harmonic oscillator model. Okay. So let us do that. So let us say that so this is basically the first thing is the ionic and electronic polarization at microscopic level. So assume that, so first what we do is that we assume that the charged dipoles behave like a linear harmonic oscillator. Okay, this is the assumption that we make to begin with. So if they do that, then they also follow the equation of motion. So when we write, now we have to write that what is the equation of motion in response to a force, right. So you have applied force, as a result they will have certain acceleration, they will have a damping component, and so on and so forth. So let us say in this case the driving the force applied is basically, you can say, is due to applied electric field, right. So when we write now the, so which is equal to, let us say, QIE. So this F is nothing but the QIE. So QIE is the force applied, this is equal to the mass of entity, that is Mi, and so it could be electrons with respect to the nucleus, or it could be ions in case of ionic polarization. So this is basically mass of the particle, you can say. Mass of particles, so it could be charges or ions, all right. So mass multiplied by acceleration, which is x double dot, right, and this is equal to, this is aided by Mi star, let us say. So we write this as a star, and then we write Mi to gamma I into dx by, sorry, if I am just writing in the notation, so then I write it as x dot. And what is this x? X, so here we write x as a displacement from equilibrium, right. Okay. So x double dot will mean basically acceleration, or you can say this is d2x by dt square. And the second thing that will happen is every system harmonic oscillator will feel friction. So as a result, there will be a friction coefficient gamma, which is gamma I, and this is nothing but gamma I into m multiplied by velocity, which is dx by dt. This is from classical mechanics. And then we have another term which is essentially mi star into omega oi square into x. And the third term is basically, if it is a simple harmonic oscillator where the charges are connected through a spring, there will be a restoring force, all right. So, there will be acceleration, there will be a restoring force, and there will be a damping. So, the first term basically is due to, you can say this term is because of acceleration, right. The second term is because of, you can say, damping or frictional force, right. And the third term is because of restoring force. So, essentially this is nothing but kx. So, we have converted this into m omega square x. So, here omega oi is the natural frequency of the particle. So, we can say omega naught I or oi is natural frequency of the particle I. Okay. And x is the displacement. So, we can write this equation, alternatively you can write this as q I e is equal to m I star into d2x by dt square plus m I gamma I into dx by dt plus m I star into omega naught I square into x. This is the equation of motion which will be in this. So, you will have applied force. In response to applied force, you will have acceleration. Every particle will feel acceleration, and then you will have damping, and you will have a restoring force because of the spring and that through which it is connected to, which we assume. Okay. So, this field is basically the field that we actually apply, that the molecule will feel or the system will feel, will be a local field that is there at present. But for the sake of simplicity, and the local field in dielectrics could be slightly different as compared to the applied field, but for the sake of simplicity we will take it as a applied field itself. So, we can assume that you have a system in which just like a gas in which there are n atoms per unit volume, and you consider them to be non-interacting. So, if the dipoles were interacting, then the field would be different, but we assume that dipoles are not interacting, and as a result the field is same as applied field. So, we can say that system is non-interacting system. So, as a result we will have local field which is same as applied field. Okay. So, now you consider two cases. So, the first case is you apply a DC field and then switch it off at a given moment. Okay. What will happen when you switch off the electric field, which is DC, the restoring forces will pull back the charges to equilibrium. So, basically you will have restoring forces, they will establish equilibrium by pulling the charges back to their original positions, and if there is no friction in the system, there is no damping, as a result there will be no damping of oscillations, and if you have friction in the system, you will have damped oscillations. So, depending upon friction, we will have damped oscillations or not. Okay. So, this is the case of DC field, which is not very interesting because we are not interested in DC field, and we know that in DC field there is no frequency dependence there. So, we will have something like ohmic losses in the system. And now, second case that is there is when field is like this. So, when field is E is equal to E naught exponential of I omega t, it is a sinusoidally varying field. So, if you have field which is sinusoidally varying, then it is likely that the displacement will also vary sinusoidally. So, the x displacement is also expressed as x naught exponential of I omega t. So, if you ignore the transient terms, students who are more interested, they can go through the solution by themselves by substituting x is equal to x naught I omega exponential I omega t. But for the sake of simplification, for the sake of saving time, we just write the solution as x t will be equal to q I into E naught exponential of I omega t divided by m I star into omega naught I square minus omega square plus I gamma I omega. This will be the solution of the above equation that we have just written in the previous page. So, assuming that field is sinusoidally varying, if field is sinusoidally varying, it is likely that the response will also be the similar. So, response is the displacement. So, displacement is also x is equal to exponential I omega t. If it has this form, then you substitute this in the above equation, solve the equation, get the ignore the transient terms, and you will get this kind of solution for x. The x will vary as q I x E naught exponential I omega t divided by m I star into omega naught I square minus omega square plus I gamma I omega bracket closed. Okay. This is what you will observe. Now, what is the induced dipole moment if this is the case? The induced dipole moment mu I is equal to q I into x, right? Mu is equal to q d, right? So, this will be equal to now q I square into E naught exponential of I omega t divided by m I into omega I square minus omega square plus I gamma I omega bracket closed. Simple. And this can be represented in the form, and what is mu? Mu is equal to, we know that mu is equal to alpha E, the polarizability multiplied by electric field. So, what is it? Alpha I into exponential of alpha I into E naught into exponential of I omega t. So, this term what we have just derived here is basically the polarizability. So, this is alpha I of ith I kind of a species is equal to q I square divided by m I into omega naught I square minus omega square plus I gamma I omega. This could be electronic or ionic. The change will be in the charges will be different for electronic system and the ionic system. The mass will be higher for ionic system than for electronic system. As a result, the polarizability of ionic systems will be lower as compared to that of electronic systems. What you also have here is you have this term omega naught square minus omega square, when omega will be equal to omega I for this corresponding. So, this omega OI will mean you will have either electronic or ionic. So, this is basically you can say is the characteristic frequency at which you will have an anomaly here. The term will go to infinity, right? If you know this term, the right term, this will go to infinity, and this is where the resonance will occur. So, when your omega is equal to omega OI for electronic and for ionic polarization, that is where you will have resonance. So, here you can consider Mi could be either mass of you can say electrons, this will be for ionic polarization, electronic polarization, right, or it could be mass of ions for a ionic polarization system. And generally for ionic polarization we consider what we say is reduced mass of the system, which is given as if you have a system as m plus m minus divided by m plus into m. So essentially it is nothing but it is coming from 1 over m is equal to 1 over m plus 1 over m minus. Okay. So m plus and m minus are cationic and anionic masses, and similarly Qi will be as appropriate, that can be easily determined, and this omega OI will be natural frequency of electronic or ionic polarization. All right. And this is why you see when you plot them, you see, so I will come to the plots later on. So let us write now the polarization. What is the polarization going to be? The polarization is nothing but n into mu I. Okay. So this will be equal to, and so we know that we can just multiply by the number of dipoles. So now we know that since here we have complex terms, which means the we know that susceptibility chi was equal to P divided by epsilon naught E. Now the susceptibility also becomes a complex quantity, because your mu is complex quantity, as a result your P is complex quantity, as a result your chi will also be complex quantity. So now if you now segregate the terms, that is so we use what we call as equations, let me just see, let us go back to some previous equations. Yeah, so basically similar equations. So basically this is now, this becomes chi, and this chi is, so this is P star, so this becomes chi star, so this will become chi prime minus I chi double prime, right. So similarly you will have to resolve the P into real numbers and complex numbers. So when you do the resolution, that you can do yourself, that is a simple exercise. So after resolving the real and imaginary, so first we get the complex quantity itself. The complex quantity is chi star I. We add a term infinite. Infinite is basically star means it is a complex quantity first of all. So that is why we write polarization as a complex quantity. Infinite is a term which is written basically, these are the susceptibilities or dielectric constants below natural frequencies. So natural frequency, since we will see we will have a resonance like this. So when you measure them below the natural frequency, it means it is chi I infinity. Okay. So that is a nomenclature thing, but so basically chi I infinity can be written as n into Qi square divided by mi into epsilon naught into 1 divided by omega naught I square minus omega naught square plus I gamma I omega. This is simple, right? It is nothing but P divided by epsilon naught E. The E will cancel each other, as a result we will have this term, and from this we can determine epsilon r. So we know that chi was equal to epsilon r star minus 1. So epsilon r star will be equal to 1 plus n into Qi square divided by mi into 1 over omega oi square minus omega square plus I gamma I omega. All right. So, as it turns out that for electronic polarization, omega OI is of the order of 10 to the power 15 second inverse, or you can say hertz, and for ionic polarization, so these are approximate numbers, omega OI is approximately 10 to the power 13 hertz or so. Okay. And you can see that for the calculation of susceptibility and electric constant, you have to use the frequencies which are lower than the natural frequency for electronic and polarization, assuming that this damping term will be very small, negligible. So, when you plot these, so from this you can also determine what is epsilon r. So, this is equal to epsilon r prime minus I epsilon r double prime, right, epsilon r. So, now you have a I term here. So, what you will do is that you will separate these variables into real and complex parts. When you do the separation into real and complex parts, you will find epsilon r infinity for ionic and electronic as n qi square divided by mi epsilon naught into omega I OI square minus omega square plus omega I square minus omega square to the power 2 plus gamma square omega square. Okay. And the real imaginary part will be n qi square divided by mi epsilon naught into gamma omega divided by omega naught I square minus omega square to the power 2 into gamma square omega square. A simple separation of variables. Okay. So, when you plot this now, what you will obtain is something like this. When you plot dielectric constant, so this is epsilon r infinity, okay, as a function of frequency, we will see it goes, if we just expand it around this point. So, this will be your omega naught electronic, for example. Okay. So, this is for electronic. Similarly, or it could be for omega naught ionic, depending upon the masses and charges. And when you plot epsilon r double prime infinity, we will see at this point system shows there will be a high loss. Okay. This is the reason why we see those resonances in the dielectric constant plot. So, we will dwell upon this a little bit more in the next lecture, but what we have established is a simple framework to calculate the dielectric constant, the complex dielectric constant on a microscopic scale for electronic and ionic polarization. Okay. Thank you very much.